In Chapter 7, we're going to change gears a little bit. Pretty much all of Chapter 6 focused on applications of integration, and once we got those integrals set up, most of them are pretty easy to evaluate. Here in Chapter 7, we are going to focus more on being able to evaluate new types of integrals that we have not seen before, or that we have encountered before, but we've had to type in our calculator to help us out because we haven't learned any new approaches besides integration by substitution on how to evaluate these different integrands. So section 7.1 really doesn't have any new calculus tricks in it. 7.1 just points out some not so obvious algebra techniques that you could use to help rewrite your integrand so that it is something that is more obviously integrable. And sometimes that's all we need to do is just apply some algebra concepts, but sometimes these algebra concepts are not so obvious when you look at them. So hopefully we'll go through a few of them here, and it will, when you see them in practice, they might be a little bit more obvious to use. So the first one I want to look at, well, let me first write that these are basically just going to be algebra and trigonometry approaches. There really is no new calculus at all here in 7.1. So the first one that we are going to look at has to do with when your integrand is a fraction. Sometimes all you need to do to simplify it and get it rewritten into something that you do know how to integrate is to just split up the numerator. Sometimes just splitting the numerator into pieces will make it so that you can simplify it and then possibly integrate it. So as an example, and this works for algebra or an algebraic expression that has trigonometry in it, I'm not going to integrate this one, but just so you can see how this could possibly work, if we had cosine x plus tan x all over sine x, and we were asked to integrate that. Now again, we're not going to do the integration yet. I just want to show you how the splitting the numerator works. With techniques that we know so far, if we were asked to integrate that, we don't see any composites, but I do see division. So the question that we ask ourselves for u substitution is, do we see products, quotients, or composites? So we do technically see a quotient here, a fraction, a division problem, but doing a u substitution for the bottom is not going to cancel the top. So when we do u substitution, our goal is with the substitution of the u and the du that all of the x's are going to eventually get replaced with u's, and that would not be the case here if we tried to do a u substitution. What we instead need to do is split apart the terms in the numerator and give them each that denominator. So this fraction says that we need to divide cosine x by sine x and tan x by sine x. So you're allowed to split up the numerator if the numerator has multiple terms. You are not allowed to split up a denominator. So if you think back to what the rules for adding fractions are, if the denominators match, you are allowed to add the numerators. So that goes back to just algebra rules with how we combine fractions. So we can split apart our numerator there into two separate fractions and then simplify this. So cosine over sine, that is equal to cotangent. Tangent over sine might be a little bit more difficult because we're going to have to think of tangent as sine over cosine, and then the whole thing is divided by sine. And then instead of dividing by sine, we can bring it up and multiply by 1 over sine. Dividing is the same as multiplying by the reciprocal. And then we'll see that those signs will cancel. So this just ends up as 1 over cosine. But 1 over cosine is itself a different trig function. We could write that as secant. So cosine x plus tangent x all over sine x really could be written much more simpler as cotan x plus secant x. And that's one example of how we can split apart our numerator in order to integrate, where we possibly see a division problem, but u substitution is not going to help us. So let's look at one where we do have to split up the numerator, but we want to go through the full integration. So we want to integrate 4 plus e to the 5x all over e to the 3x. Now, it is a quotient again, so that is the first indication we might want to try u substitution, but if we do a u substitution for our denominator, e to the 3x, the derivative is also going to have an e to the 3x in it, and my numerator does not have another e to the 3x to get rid of. So u substitution is not going to work here because the two functions we're dealing with, our numerator and denominator, do not have like a du over u relationship. So what we're going to do instead is we're going to separate these and then just use algebra to try to simplify them. So this is really 4 over e to the 3x plus e to the 5x over e to the 3x. And both of those could be simplified. So now this is 4e to the negative 3x. We can pull that up with a negative power. And then in our second one, we've got common bases, which means we can combine our numerators. And laws of exponents say we would subtract the numerators. So 5x minus 3x is 2x. This function now, 4e to the negative 3x plus e to the 2x, we can easily integrate. Because remember, one of the shortcut rules for integration when you have a linear coefficient, or excuse me, a linear exponent, is you are just going to divide in front by the derivative of that exponent. That only works if your exponent is linear, which in this case they are. So when I say linear, I mean we've got just some coefficient times x. So for both of these, in order to integrate, I just have to pull out the derivative of my exponent into a fraction in the front. So we're going to get negative 4/3 e to the negative 3x plus 1/2 e to the 2x plus c. And all we have to do is recognize that we can split apart that numerator into two pieces and think of it as two completely separate terms. And the terms will simplify nicely, and then it's not a quotient problem anymore. I want to look at one more of these before we move on, because this one at first glance looks a lot trickier and doesn't look at first like it's something that you are going to want to separate. But we are going to integrate 2 minus 5x divided by the square root of 9 minus x squared. I do see a composite function here, and I see a quotient. If you were to try to write out the u substitution with u equal 9 minus x squared, the du would be negative 2x, which helps us for one of the terms. But right now, those two terms are combined into a single expression. That is the key that tells me, if I could split these two guys apart, u substitution would help me with the 5x. It's not going to help me with the 2, but it will help me with the 5x. So we are going to take our denominator and split it amongst our numerators, the two terms in our numerator, and think of this as 2 over the square root of 9 minus x squared minus 5x over the square root of 9 minus x squared. And the u substitution that we just talked about will work on the second term. It won't work on the first term because the derivative has an x in it and our numerator does not. This type of integral we see here in the first term is something that we're going to address in a lot more detail in section 4. For right now, though, we do very, very quickly kind of glance over this type of integral in Calculus 1. I don't emphasize it so much in my class because I know as we get to Calculus 2, we're going to learn a much better, more concrete way to evaluate it. But this integral is going to turn into arcsine. So back in chapter 3, we learned some of the trig inverse derivatives, and of course derivatives and antiderivatives are just opposite operations. So the one that we're going to use in our textbook on page 217, and I'm going to write down what 217 says, but then I'm going to write a more general form. The derivative for sine inverse of x is equal to 1 over the square root of 1 minus x squared. So that looks very similar to what we have here. The only difference is we have a 2 in our numerator, which is easy to take care of. We can think of that 2 as just a coefficient, and we have a 9 in our denominator. So we need to talk about what to do with that 9. So it's more common to see the antiderivative representation of this function written a little bit differently. The link between the two has got quite a few algebra steps and a u substitution, but we would see this as the integral of 1 over the square root of a squared minus x squared, which is what we have in ours. And this is going to turn into arcsine because we see that difference of squares in the denominator under that square root. But this formula is going to be a little bit more helpful to help us decide what to do with the a if there's a number in front. And what we do is we take the square root of it and we put it underneath the x in our angle, or excuse me, not our angle, in our trig value. So this is what we are going to use. Again, don't worry about knowing these inverse trig formulas. We're going to talk a lot more about them in 7.4 and learn a much better way to figure them out without having to memorize them. I just know there's possibly some problems in this section that use them. So this one's specifically for arcsine. And this is the one that we are going to use. Excuse me, we should not have 3 there. We would just put an a there because we had a in our formula. When we apply this to our problem up here, the a value in fact is 3, so we'll use a 3 there. But anytime we have the integral of 1 over the square root of a squared minus x squared, it turns into arcsine of x over a. So that's what we need to do for the first part. So if we continue the integral down here, I know the first piece is just going to turn into an arcsine. The 2 is just a coefficient, so I've got 2 arcsine of x over 3, because we've got a squared and x squared in our integrand, but when we transfer it to our answer, it's just x and a. So we take the square root of both pieces. And then minus, now we said on this piece, the whole idea we got for separating is that u substitution would take care of that second term. So we should write out our u substitution so we can see what it's going to look like. We would let u be the inside of the composite piece. Du will be negative 2x dx, which means negative 1 over 2x du will equal dx. That's what we're going to replace our dx with. So for the second part of this problem, I'm not ready to integrate. I'm just writing it in terms of u. So we've got 5x over the square root of u, and then instead of dx, we're going to write negative 1 over 2x du. And we see that those x's cancel, which is perfect, because then it just turns into something we can evaluate with a power rule. I'm going to go ahead and put those coefficients together and say this is negative 5/2, and I'm going to move it to the front. So this is going to be plus 5/2 times the integral of u to the negative 1/2. That means square root in the bottom. And we could easily integrate that piece just with a power rule. So it's going to go up to u to the positive 1/2. And then remember, with power rule with antiderivatives, we take our new exponent and we flip it out front to multiply with our coefficient. So 1/2 flipped is 2. And this just ends up as 5 times our u to the 1/2. So 5 square root of 9 minus x squared. So our final answer, we ended up having to do two antiderivatives because we split our fraction into two terms, is 2 arc sine of x over 3 plus 5 square root of 9 minus x squared plus c. So this one's a little bit trickier because the integration we have to do still is kind of tricky, but it still uses the same concept where we really can't do anything until we split apart those terms in our numerator. So this first concept we talked about was always look to see if you can split the numerator. The second concept that we are going to talk about also has to do with fractions, but we're not going to be splitting apart the numerator. Splitting apart the numerator is usually only when your denominator is a single term, but if you see that splitting apart the numerator is not going to help that fraction, and you're working mostly with polynomials, you might want to consider using long division, polynomial long division. Which you probably have not done in quite a while, depending on how long ago you took pre-calculus algebra. So again, to start with, we're not going to look at an integration problem, but why we might want to do this is if we were asked to integrate x squared plus 12x minus 2 over x plus 1. Now, x squared plus 12x minus 2 does not factor, so we don't really have any hopes of canceling the x plus 1 after factoring. We also, because it's a quotient, whenever we have a quotient, we typically look to the denominator for our u, and when we do u substitution. If we were to let u equal x plus 1, du would not do anything to our numerator because du is just going to equal dx. So it's not going to get rid of anything in the top. But this is an improper fraction. So that's one of the things you can look for that gives you a clue that you should probably try polynomial long division, is you're asked to integrate an improper fraction. And what that means is that the degree in the numerator is bigger than the degree in the denominator. That means we can use algebra to simplify this fraction. So we're going to do polynomial long division. We'll review that really quickly, and then we'll look at an actual integration problem where we would have to use this. Now, in polynomial long division, for the division step, you only look at the leading term in your divisor and the leading term in your dividend. And we're asking ourselves, how many times does x go into x squared? Or, if you want to frame it more as a division question, what is x squared over x? So that's the first division we do, x squared divided by x. And that's equal to x. Now, once we get the division done, we're going to multiply down and subtract. And when you multiply down and subtract, you use everything. So when I multiply down, I'm going to have to multiply by the x and the 1. So x times x is x squared. X times 1 is x. And we need to subtract this stuff, because we have just accounted for it in the division by saying that x into x squared goes x times, when technically we're trying to do x plus 1 into this polynomial. So we will subtract, make sure that your like terms are lined up so you're combining correctly. I don't have anything to combine with my negative 2. 12x minus x is 11x. And then x squared minus x squared, they go away. And that should always happen. That first term should always go away, otherwise you did not divide correctly. And then we have a second division we can do. Now, these are our leftovers, and this is what we continue working with. We want to know how many times x will go into 11x, or if you frame it as a division question, what is 11x divided by x? And that's a lot easier to simplify and see the answer is going to be 11. So the next part of my answer in the division is going to be a positive 11 or plus 11. And then we're going to multiply down and subtract. So 11 times x is 11x. 11 times 1 is 11. And we need to subtract this stuff. And that will tell us what we have left over to continue working with. So just like I said a minute ago, those first two terms should always cancel out. Otherwise, we did the division wrong. And they do. We've got 11x minus 11x is 0. And then we'll put our constants together. I've got negative 2 minus 11 is negative 13. Now you can check, but technically we're done. Because the next one that we would do is we would say, all right, how many times does x go into negative 13? Or as a division question, negative 13 over x. That cannot be simplified, which means we're done with our division. So the way that we write our remainder is we say minus, I'm doing minus because it's a negative 13, 13 over x plus 1. We still have that division problem left to do, but with this way that we're doing it, we can't, since we don't know what x is. So we're just indicating we still have that much more division to do. We just can't continue any further. We are able to simplify out the x plus 11, but there's still a 13 in there, a minus 13 in there. So this is the solution to just the division problem. And if we were asked to integrate, this would be much easier to integrate than the original. So now let's look at a quick integration problem. So if we were asked to integrate, and this one's going to be very similar, we can get some more practice with that long division. Let's try to integrate x squared plus 5 over x minus 2. U substitution is not going to work on this, again, because in quotients we get the u from the denominator. There's no composites here, so we wouldn't get the u from the inside of the composite. If u is x minus 2, du is going to be dx, and that numerator is going to be completely left alone. And when we rewrite it, we'll still have u's and x's in the problem, so that's not good. But, like I said just a minute ago, this is an improper fraction. The degree in our numerator is larger than the degree in our denominator, which means we could possibly get this simplified with some long division. Now when we do the long division, if you want to, there is a term missing in the numerator. I go straight from my squared term down to my constant. Typically there is a linear term there, and if it's missing, that just means we have 0 of them. And it might be helpful for you to go ahead and write that in case we end up with any linear terms in the division process that we need to subtract. So in the division step, you only look at the leading terms. X goes into x squared x times, and then we'll multiply down. X times x is x squared. X times negative 2 is negative 2x. And then we need to subtract this. So we change the signs. And then we can combine. So those guys cancel. And I've got 0x and 2x is 2x. And there's nothing to combine with my 5, so I'll just pull it down. And then we go through the whole process again. Now we're going to say, all right, how many times does x go into 2x? And it goes in 2 times. And then we'll multiply down and subtract. 2 times x is 2x. 2 times negative 2 is negative 4. But we're subtracting this stuff, so we change the signs. And just as we expected, the first terms are going to cancel. And when we combine those constants, we get 9. And x will not go into 9 because 9 has no variables. So 9 is our remainder. Because it's positive, I'm going to say plus 9 over x minus 2. Now this is going to be much easier to integrate. So this is an equivalent integration problem. All I've done is used some algebra to rewrite my integrand as x plus 2 plus 9 over x minus 2. So the antiderivative for x is 1/2 x squared. The antiderivative for 2 is 2x. And then in order to do this piece, it still is a quotient. It's a much easier quotient though. Now when we do u equals x minus 2, du equals dx, all the x's go away, which is perfect because that piece does not have any x's in the top anymore. And we're left with the integral of 9 over u, which turns into natural log. So we've got 9 times the natural log of the absolute value of x minus 2.